the silent, pressurized depths of the world's oceans, the survival of a 100,000-ton sovereign territory depends on a single point of failure: the ground tackle. We often conceptualize the aircraft carrier as a symbol of kinetic power, a 333-meter engine of power projection capable of launching 90 aircraft into the fray. Yet, its most critical defensive posture is one of absolute stillness. When a Nimitz-class supercarrier prepares to drop anchor, it is not merely tossing a weight overboard. It is initiating a high-stakes mechanical sequence involving the management of massive potential energy. The anchor, a 30,000-pound, 13.6 metric ton Castile behemoth, serves as a terminal point of a chain so massive that every single link weighs up to 136 pounds. This is the anchor drop test, conducted at full speed in naval terms, meaning the maximum control velocity allowed by the windlass braking system. This procedure validates the integrity of the Wildcat drums and the hydraulic friction brakes. A failure here is catastrophic. If the brake fails to seize the chain, the Wildcat will spin out of control, potentially ripping the chain locker out of the ship's internal structure or causing a friction fire that can melt high-carbon steel links. We are looking at the convergence of 18th century nautical fundamentals and 21st century metallurgical science. To understand how the Navy stops a moving mountain, we must first look at the anatomy of the abyss. Why does a ship of this magnitude require such an extreme anchoring system? The answer lies in the variables of the maritime environment, current, windage, and displacement. A supercarrier has a massive sail area, the physical surface of the hull and island exposed to the wind. In a 40-knot gale, the lateral force exerted on the vessel is equivalent to millions of newtons. Without a secure tether, the ship becomes a drifting hazard to navigation. The catalyst for the sophisticated drop test is a requirement for emergency anchoring. While ships typically anchor in calm waters at slow speeds, combat or mechanical failure may necessitate a crash stop. The mechanical sequence begins in the windlass room on a modern carrier. Two primary windlasses are located at the bow. These are not simply winches. They are massive hydraulic or electric prime movers. The heart of the system is the Wildcat. Unlike a smooth drum, the Wildcat is a 5-wheeled sprocket designed specifically to mate with the geometry of the anchor chain links. The mechanical sequence begins in the windlass room on a modern carrier. Two primary windlasses are located at the bow. These are not simple winches. They are massive hydraulic or electric prime movers. The heart of the system is the Wildcat. Unlike a smooth drum, the Wildcat is a 5-wheeled sprocket designed specifically to mate with the geometry of the anchor chain links. Technical specifications of the gear: chain length, approximately 1,440 feet, 240 fathoms. Weight per link, 120 to 150 pounds. Brake strength, exceeding 2 million pounds of linear tension. The drop is a controlled freefall. The bosun's mate BM releases the brake, allowing gravity to accelerate the 30,000 pounds anchor. As the chain screams to the hawse pipe, it creates a cloud of rust and pulverized paint, a phenomenon known as smoking the brake. The BM must apply the brake at specific intervals, typically at the 15, 30, and 45 fathom marks, 90, 180, 270 feet. This validates that the friction linings can dissipate the heat generated by the descending mass. If the friction coefficient of the brake pads is degraded by salt spray corrosion or hydraulic fluid leaks, the chain will run away. A runaway chain is a death sentence for the equipment. Once the momentum exceeds the braking capacity, the chain will continue until it reaches the bitter end, the point where the chain is shackled to the ship's structure. If the bitter end fails, The entire 1,440-foot chain is lost to the sea. If it holds, the shock load can buckle the carrier's internal bulkheads. To understand the how, we must analyze the material. The anchor chain is not standard steel. It is grade 4U4 or grade 5U5 ultra-high-strength cast steel. These alloys are specifically engineered to resist stress corrosion cracking, SCC, and hydrogen embrittlement caused by constant immersion in salt water. An anchor does not hold a ship by its weight alone. In fact, the weight of the anchor is only about 10 to 15% of the total holding power. The real anchor is the catenary curve of the chain. The science. As the chain lies along the seabed, the friction between the heavy links and the silt/sand creates a massive resistive force. The math. For a ship to stay moored, the length of the chain deployed, the scope, must be 5 to 7 times the depth of the water. This ensures the pull on the anchor itself is horizontal, allowing the flukes to dig deeper into the substrate. This is a terrestrial cousin to the carrier's Mk-7 arresting gear. When a 30,000 pounds fighter jet hits the deck at 150 knots, 277 kilometers per hour, it possesses roughly 60 million joules of kinetic energy. Stopping this mass in under 300 feet requires a feat of hydraulic engineering. The BAK-12 uses a rotary friction brake system. Impact. The aircraft's tailhook snags a pendant to steel cable. Transfer. The pendant is attached to nylon tapes wound around 2 large reels. Dissipation. As the tapes unwind, they spin a series of rotors inside a fluid-filled housing. The kinetic energy is converted into heat via fluid shearing and mechanical friction. Max engagement speed, 190 knots. Maximum weight capacity, 65,000 pounds. Tension control. A static brake is not enough. The system uses a cam-operated valve to increase braking pressure as the aircraft moves down the runway, ensuring a constant, survivable deceleration rate G-force for the pilot. The video highlights the manual check. Every link of the anchor chain is inspected for pitting and diameter reduction. If a link loses more than 10% of its original wire diameter due to corrosion, the entire shot, a 90-foot section, must be replaced. Similarly, the BAK-12 tapes are replaced based on cycles or age, as UV radiation degrades the polymer strength of the nylon. Whether it's a 30,000-pound anchor holding a carrier against a hurricane or the BAK-12 cable saving an F-16 with a blown engine, these systems represent the ultimate Plan B. They are the silent guardians of naval aviation and maritime safety. Military engineering is often defined by the ability to destroy, but the science of the anchor and the arresting gear is defined by the ability to preserve. In the high-velocity world of modern warfare, the most valuable technology is often the one that can bring a Titan to a complete, safe, and absolute halt.